let's start with the egg. So this is the phase diagram of an egg. We've showed this to you many times. As you increase the temperature, we've told you that there are different protein components that unfold and bind to each other to form the cross-links. So now let's examine in a little bit more detail how this actually happens. So the egg white, let's just start and consider the egg white. The egg white consists of a sea of proteins. There are little molecules that are proteins that are clumped together into little clumps. Each protein in solution is, when you put it in at room temperature, in a sort of compact clump, sort of folded together. When you heat the egg at some temperature, what happens is the protein unfolds and actually becomes more like a stringy polymer. And what you actually have then in solution is a sea of different polymers that are floating around. Now, it turns out that these polymers are sticky. That is, they're not, once it unfolds, they're actually sticky, and they stick to each other, and it's the sticking to each other of the polymers that causes the cross-links in the egg, and that's the reason that an egg solidifies when you heat it. The reason, by the way, that when you cool an egg, it doesn't unstick and doesn't go back into a liquid is because these cross-links are so strong that when you cool it back down, they don't break back and the proteins don't unfold. The process is essentially irreversible when you do it the way that we tend to cook. So the next question is, why is it that proteins are sticky when they unfold? And to sort of understand this, we have to remember what proteins are. So proteins, you will recall, are polymers, which are chains of amino acids. So there are 20 different amino acids, and a protein is composed of some sequence of different amino acids. Depending on the protein, there will be a different sequence. Now, amino acids have different properties. This is a list of the 20 different amino acids that there are. They have names that range from aspartic acid to lysine to glutamine and so on. And each of these different amino acids has different chemical properties, but it also has different physical properties. And there are two types of physical properties that we want to focus on right now. Just as an example, so it's now possible, in the modern era, to find out what sequence of amino acids corresponds to any protein. So this is the sequence of amino acids that corresponds to chicken of albumin. Each of these letters refers to one of the amino acids that I just discussed, and that is the major component of egg whites. So now the amino acids have different properties, and I would like to start by focusing on two of them, because these are, in a certain sense, the most important for explaining why the different proteins stick to each other. There are some amino acids which are called hydrophilic, and there are others which are called hydrophobic. So a hydrophilic amino acid is one that likes water. Hydrophilic basically means that it likes water, whereas hydrophobic, it's phobic of hydro, namely water, doesn't like water. So if you put hydrophilic amino acids in water, they're perfectly happy. If you put hydrophobic amino acids in water, they're perfectly sad. They don't like being surrounded by water, but they have no choice. And their goal in life is really to cover themselves as much as possible so they don't have to contact with water. Now, they also don't like hydrophilic amino acids because hydrophilic amino acids like water. So essentially the deal is that if you have a protein which has a bunch of hydrophobic amino acids, what they will try to do is clump together and stay away from water as much as possible, whereas the hydrophilic amino acids are happy being near each other and being in the water. So with this as context, this picture right here is a toy model of a protein chain. So this protein chain has on it black dots and white dots. And for the sake of argument, let's say that the black dots are hydrophobic. So these are amino acids which don't like water, whereas the white dots are amino acids that do like water. So if I show you this string, then the question is, what's going to happen to the string? Now, if the temperature is low, so that the protein doesn't want to jiggle around, it will try to fold into a compact clump, and it will do that by basically clumping all of the black dots, the hydrophobic amino acids, together so that they touch each other where they're happy, and it will also move them to the inside of the protein where they're away from the surface and thus don't want to touch water. You'll put all of the hydrophilic ones on the outside surface. They can contact water, and you shield the hydrophobic ones so that they don't touch the water. Now, of course, it's not possible to do this perfectly because, that they're also all attached to a string, so you might end up with some hydrophobic bits on the surface, but you try to minimize that as much as possible when you fold the water. And in fact, the principle of minimizing the free energy of the protein leads to this configuration as the most favorable state when you're at low temperatures. Now, when you're at high temperatures, then actually the entropy, starts to matter, and the protein unfolds. It unfolds because it likes jiggling around. Entropy, as we've discussed before when we were describing phase transitions, competes with energy and causes the protein to unfold. And once it does that, then all of these black hydrophobic amino acids that were initially buried inside are exposed and open for business. The business that they're in, of course, is sticking to other hydrophobic amino acids. And so what happens is that the different unfolded proteins bind to each other, causing cross-links, which is what forms the gel when you cook an egg. So we can see this in sort of toy models. It's also possible to do simulations of full proteins unfolding, and we just want to give you a little bit of dose of reality. So this is a simulation that was done of a real protein that is unfolding, in which, and this is a molecular dynamics simulation that actually includes all of the forces and other things that we understand that are going on. And you see that so initially in its compact state, the protein has lots of helices in them and sort of bends, and these are characteristic structures that proteins tend to have. And when you heat it up, you see that the bends and everything go away and the protein unfolds. The hydrophobic residues are open for business, for sticking to others. So heating isn't the only way to cook an egg, and for that reason, it's interesting to think about other ways of even within the simple case of an egg, causing this protein unfolding and sticking transition. And so if you look at recipes, it turns out there are two other ways of actually causing transition in eggs. One is by changing the salt concentration, by actually putting salt. That can affect the way that proteins fold. And the other is by changing the pH. And I want to start by demonstrating that in the simple recipe for a poached egg. So in this recipe for a poached egg, if you look at the recipe, what it calls for is 1 tablespoon of vinegar and 4 very large eggs. So before you cook the eggs, you actually pour vinegar in the water. And then what the recipe says is really quite shocking for those of us who cook eggs on a regular basis, which is it tells you to boil them, but only for 2 to 3 minutes, which is a very short cooking time. And it claims that if you do that you still will be able to cook the egg. So it turns out that when you put vinegar in water, what you are actually doing is changing the pH of the solution. So you're changing the concentration of hydrogen ions in the solution. And in fact, you're increasing it quite dramatically when you put vinegar in the solutions. So why does this make a difference? So if we go back to the table of proteins and their properties, we so far have emphasized that there are some proteins that are hydrophobic and others that are hydrophilic. But there's one more important property that is worthy of mentioning, which is that some of the amino acids have negative charges. So aspartic acid and glutamic acid have negative electric charges, whereas arginine and lysine have positive electric charges. And electric charges, of course, are another way in which the amino acids on the protein can interact with each other. So if we go back to our little picture of proteins from before, the protein had black dots and white dots, which referred to hydrophobic and hydrophilic amino acids. But some of the amino acids are also going to have electrical charges. So some of them are going to have positive charges, some of them are going to have negative charges. Now, basically, the way that physics works is that like charges repel each other and unlike charges attract. So if you put a positive charge next to another positive charge, that causes a force that causes the thing to blow apart. Whereas if you put negative charges next to a positive charge, they'll like to come together. And there is, in fact, an electrostatic energy of the system, which is proportional to essentially the square of the charges that contribute to the free energy of the protein in solution. Now, of course, when the protein is folded up, it's already compensated for these charges. And when you heat it up, it unfolds, compensating again for the charges. But it turns out that one thing that you can do to sort of manipulate when proteins fold and unfold is to actually change the charges of the protein while they're in solution. And the way to do that is to change the pH of the medium. Because you see, it turns out that when we say that amino acid is charged, the charged amino acids change their charge depending on the pH that they're in. And so what we can do is, if we make the solution more acidic, therefore, we can make the charges more dramatic than they were before, and thus the proteins become easier to unfold. It is similarly the case that if we make the solution very basic, if we actually make the pH closer to 14, push it in the basic direction, then they also acquire a much more dramatically different charge than they would have otherwise. So one simple way of seeing this in the context of cooking is that we can make a plot that I will show you right here. And for now, we're not going to tell you how to make this plot, but this is a plot that can be made by taking the amino acid sequence of a protein and having an understanding of the charge state of each of the amino acids as a function of pH. So what you do is you go into the amino acid sequence and you simply count the number of positively charged amino acids there are, aspartic or glutamic acid, or negatively charged amino acids, histidine and the like, and then simply count the number that there are and take into account their pH dependence and thus get thus calculate the dependence of the total charge on the protein as a function of the pH. Here is the plot for fish myosin. So this is an important component of fish, which is presumably important when cooking fish. And what you see here is that at neutral pH, the charge is some intermediate value. But when you make the solution highly acidic, that is, say, around 2, the charge state of the protein goes up dramatically. It goes up by several fold. And that, of course, makes the protein much more unstable and will make it much more likely to unfold. So that makes it much more likely to undergo from the uncooked transition to the cooked transition that we're all familiar with when we cook fish. So similar sorts of transitions occur when you cook an egg. If you go to a very basic solution, for example, by putting vinegar in the solution, the net charge on the protein goes up dramatically. So this, of course, raises the question, if you wanted to actually manipulate the pH of the solution, then how would you do it? And this is a table of different materials that one could imagine using when cooking, and with the typical values of pH that they have. So water, of course, pure water has a pH of 7. Vinegar, which is what we were using in the poached egg recipe, has a pH around 2.4, and lemon juice is around 2.2. Gastric juice, which is the material in your stomach, that's highly acidic. That has a pH around 1. On the more basic side, you could add toothpaste to the food that you're eating. That, it turns out, has a pH of around 9.9. Baking soda is a more common cooking ingredient. It has a pH of around 8.4, and so on and so forth. Now, the thing is, and one of the challenges when manipulating the pH while cooking, is that, of course, we don't just want to cause the proteins to unfold and coagulate. We also don't want to mess up the taste. And if any of you have ever had a spoonful of vinegar, you will note that it doesn't taste very good. So when you're adding vinegar to your egg, or for example, vinegar is one of the essential ingredients for cooking ricotta cheese, you have to make sure that you add only a little bit so that it doesn't affect the taste. And this is sort of one of the balances that we have in cooking between, on one hand, causing transitions by changing the acidity, and on the other hand, causing them with temperature. When we change the acidity, we also tend to affect taste.